Hi all, we are learning about nuclear radiation today. So nuclear radiation, up here is your title. You're going to be learning about 3 different types of ionizing radiation, which are examples of nuclear radiation, how we can detect them, what materials can be used to stop them. You need to know what order they are in terms of their penetrating power. And we'll be looking at why ionizing radiation can be dangerous. So as your do now task, just jot down 3 things you might think you already know about radiation, because you've probably heard of the word radiation already, and then you've got your keywords at the bottom to jot down as well. So the screen could be paused while you do that. I'm just going to get rid of that. And I'm going to move the keywords up for you too, which I meant to do before. That wasn't good. Sorry, I should have done that before I started recording. There we go. So the slide could be paused here just to let you get that done. So I'm going to move on now. I'm guessing the sorts of things you might have written about radiation are things like it's quite dangerous, it can cause things like cancer. Those are indeed true. This is a man called Alexander Litchinevenko, I think his name was. He was a Russian agent who defected, who left Russia and came to the UK some years ago. He died due to radiation poisoning in 2006, and it was big headlines. You won't remember because you were tiny, if here, but it made the headlines because it's believed that two Russian agents actually came over to Britain to meet with him and put radioactive polonium in a cup of tea, I think it was, and poisoned him. Because he had left Russia and then spoke quite badly about the Russian government. And so it's thought that he was poisoned deliberately as a way of keeping him quiet and sort of setting him up as an example to warn other people off doing the same. So that's pleasant. Anyway, moving on. So the word radiation in everyday life usually means something sort of spreading out or being given off from a central point. So when we talk about nuclear radiation, we're talking about either particles or waves that are being emitted from the nucleus of the atoms in a radioactive substance. So it's the nucleus at the centre of the atom that is giving off something or radiating something, and it's usually in the form of a particle or an energy wave. So this happens when the nucleus itself is unstable. So in most atoms, the protons and neutrons are held together nice and tightly, and they are stable in the nucleus of the atom, and they just sort of stay put. But in some atoms, particularly atoms that have got very, very large nuclei, the protons and the neutrons aren't held together tightly, they are unstable. And the nuclei will try and get rid of bits of itself in order to become more stable. That's what we mean by nuclear radiation. So this can also be known as radioactive decay, by the way, because as the nucleus is getting rid of bits of itself, it's said to be decaying. All right, so nuclear radiation, radioactivity, nuclear decay, radioactive decay, all these terms mean the same thing. So nuclear radiation then, what is it? Well, there are 3 different types. The first type, this type, is known as alpha radiation, okay? The second type is known as beta radiation, and the third type is known as gamma radiation. So in alpha radiation, our nucleus gets rid of an alpha particle, And an alpha particle is made up of 2 protons and 2 neutrons. And it can also be known as a helium nucleus, because actually a helium nucleus does contain 2 protons and 2 neutrons. So when an unstable atom spits out 2 protons and 2 protons and 2 neutrons from its nucleus, then we call that alpha radiation. Sometimes, though, an unstable nucleus will get rid of a very, very high energy electron. That's known as a beta particle. Okay, so that would be termed beta radiation. And then in gamma radiation, we learnt about gamma rays, didn't we, when we were doing the electromagnetic spectrum? So a gamma ray is actually a form of nuclear radiation, and we get a gamma wave, also known as a photon or gamma ray, being given off. So in this instance, it's like a release of energy rather than a release of a particle, whereas alpha, beta are particles being given off. Okay, so worth pausing this and just making a note of the names of those types of types of nuclear radiation and what they are made up of. So I'm assuming you've finished. I'm going to move us on now. If I was in school with you, I'd be demonstrating using this bit of kit, a Geiger-Müller tube and a Geiger-Müller counter. I would be detecting radiation in the classroom to show you that actually there are sources of radiation all around us. We would also look at some samples of radioactive materials such as uranium, and we'd be able to see that there is a far higher radiation activity reading using our Geiger-Müller tube if we've got the radioactive sources to look at. So I'll perhaps, depending on time, that might be something we can do. Okay, so going into a bit more detail about the 3 types of radiation. And is there radiation all around us? Well, as I've said already, it's alpha, beta, gamma. Yes, there is radiation all around us, but in relatively low doses. And things like radon. Radon is a radioactive substance found in granite rock. So parts of the country where there's lots of granite in the ground have got higher levels of background radiation. But there's radioactive atoms in lots and lots of things. Some of the foods we eat are slightly radioactive. Bananas is a good example of a radioactive food. But in very, very low levels, it's not harmful. This is a map that shows us the relative radioactivity in different parts of the country. So as you can see, background radiation is measured in a unit called sieverts. And the highest, the dark reddy pink areas, the highest areas of levels tend to be in parts of the country where you've got a lot of granite in the ground. Okay, so we're going to have a look at the video. Oops. I've forgotten to set this up beforehand, which is really helpful. Okay, so if for any reason this doesn't play very well, then whoever's covering the lesson should be able to find this on YouTube.
Which is energy that's given off by radioactive materials. Ionizing radiation has a lot of energy, much more than the low energy radiation from radio waves, cell phones, and microwaves. These types of low energy radiation are called non-ionizing radiation. Ionizing radiation has potential for interacting with and changing atoms and molecules. This is an important distinction which many people may not realize. For simplicity, we'll just refer to it as radiation. If radiation hits the cells in the body, it can damage or even kill the cells. The amount of energy that the body absorbs from this radiation is called the radiation dose. At high doses, and when most of the body is exposed, enough cells die to impair the function of various organs in the body, and that can lead to really serious health effects, including death. If only a specific part of the body is exposed and the dose is high enough, it could lead to localized effects, such as skin injury. At low doses, if any cells are damaged, the cells may repair that damage with no consequence, or the cells may leave the damage unrepaired or repair it incorrectly, and these may have long-term consequences and could potentially increase the risk of cancer.
You use the word exposed. Is this term used differently for radiation hazards than other environmental hazards?
It is. When our bodies absorb the energy from radiation, we're being exposed to radiation. We don't have to come in contact necessarily with any radioactive materials. If we walk away from the source of radiation, the exposure stops.
So like with an X-ray, you're exposed while the X-ray is being taken, but you don't take any of the radiation home with you.
Exactly. Now, in contrast, if radioactive material gets on our clothing, skin, or hair, it contaminates us. We call this external contamination because it's on the outside of our bodies. External contamination can be removed simply by taking off contaminated clothing and washing with soap and water. If we inhale or ingest radioactive material, we call that internal contamination because it's now inside our bodies. It's harder to remove internal contamination. Our bodies can get rid of some of it through metabolism and excretion. And for some types of radioactive material, we have medicines. We call them countermeasures that can speed up the excretion process.
Okay. So back to our presentation then. Okay, so what do we actually mean by ionizing radiation? Well, he said on the video that ionizing radiation has got far more energy than non-ionizing radiation. And more specifically, ionizing radiation has the power to change, or the energy, to change atoms into ions. So when atoms gain or lose electrons, they form some things called ions, I-O-N, not I-R-O-N. It's not the same as the metal ion. And ionizing radiation can do that. It can actually strip electrons from atoms so that they become ions. And this can damage your DNA in your cells, and it can potentially cause cancer in healthy cells. So gamma rays are an example. That's why we use them to destroy cancer cells. They actually damage cancer cells, but the danger is that they damage healthy cells too in the course of the treatment. Same with X-rays. You might know that if you have repeated X-rays during your lifetime, that can make you more at risk of cancer. So hospitals used to do X-rays for all sorts of things. They now only do them when they're really, really necessary. Ultraviolet, which is the part of the electromagnetic spectrum that causes sunburn, is also ionizing, and that's why sunburn can lead you, and sun exposure can lead you to get skin cancer. So how can we make use of it? Well, as I've just said, we can use it to kill cancer. We can use ionizing radiation to kill cancer. We also use it to sterilize things because it will destroy bacteria and viruses. But the danger of using ionizing radiation in treatments is that you damage healthy cells. Okay, one of the things you need to understand, because it links to how risky it is to be around certain types of radiation, is what they can penetrate. So this particle represents our alpha particle here, 2 protons, 2 neutrons, and alpha particles are the least penetrating of these 3 types of radiation. So alpha particles will actually be absorbed and stopped by paper. They'll also be absorbed and stopped by skin. So if an alpha particle is outside of your body and comes into contact with you, it's actually pretty harmless if it just comes into contact with the outside of your body. It's more dangerous, though, if it gets inside your body. because it can't get out again. Once an alpha particle is inhaled or swallowed, it's in your body and it's going to cause lots of damage. But outside your body, relatively harmless. Beta particles, those are those high energy electrons. Beta particles can get through paper and skin, but if they can get through skin one way, they can get through skin the other. So they will actually go right through us, but they can be stopped by aluminium. And the most penetrating of these three is the gamma rays. So gamma rays will pass through paper and skin and aluminium, but they'll be stopped by thick lead. So if I was to show you some radioactive materials that emitted gamma radiation, they would normally be kept in, or they would be kept in a lead-lined box. So can you just jot down either in words or a quick diagram showing what's on the screen, jot down the penetrating power of these materials. So alpha particles can go through air, but they're stopped by paper and skin. Beta particles can go through air and paper, but they're stopped by aluminium. Gamma rays can go through air, paper, aluminium, and they're stopped by lead. So the video could be paused now just to allow you to get that down. And moving on. So I'd also like you to just jot down some key points about these particles. So alpha particles, they are made up of 2 protons, 2 neutrons. They are big particles in relative terms. And protons have a positive charge. Neutrons are neutral charge or no charge, which means overall an alpha particle has got a positive charge. Okay, so they're positively charged particles. They would be attracted to negatively charged particles. So alpha particles, they're big. This is how we write alpha, or you can write the word alpha. But things to know about them, they're big, they're positively charged, and they contain protons and neutrons, 2 of each. And as we said before, they're easily stopped by paper and skin, so they are not very penetrating. I'm going to move on to beta. So our beta particles, represented by B with a fancy swish, they're negatively charged particles, and they basically just consist of a high energy electron. They are absolutely tiny. And they're stopped by aluminium foil. Gamma is not a particle. Gamma is a ray. So in terms of its size, it is very, very small. It doesn't have any mass. No charge. It's not positive or negative. And it's pretty impossible to stop gamma unless you've got really, really thick lead or other metal. So there's a table there that nicely summarises the different types. So the video could be paused here just to let you get those main points down. Okay, I'm going to move us on to a video now about the 3 types.
And this It's called uranyl nitrate. If you look at it,
sorry, I'll try that again. There we go.
In 1895, Henri Becquerel, he's the man with the moustache, discovered that rocks of uranium affected photographic paper. This is the rock of uranium that he looked at, and it's called uranyl nitrate. If you look at it, you can see it's yellow. It shouldn't be yellow, that's because it's giving off light. This means that there is some evidence in the rock that there's energy being given off, which affects the paper and which gives out this light. This was the first evidence of radioactivity. However, there was no indication of what this energy source was. It was only with the discovery of other radioactive materials that a pattern started to emerge. The radiation got sorted into 3 types. We're going to talk about these 3 types now. So let's introduce the first one. Here comes alpha. Alpha radiation is very easily stopped. It's stopped by air. Look, it just goes into the air and stops. Even a piece of paper, if you put a piece of paper in front of alpha radiation, it can't go any further. It's also strongly affected by a magnetic field. So here we've got a whole beam of alpha particles, and these alpha particles are going through a magnetic field. And when they go through the magnetic field, they bend quite a lot. This tells us 2 things. One, that it's the heaviest of the radioactive particles, and 2, it's the most heavily charged type of radiation. The symbol for alpha is this, the Greek letter alpha. It's not very penetrating. That means if it actually hits something, it stops. Penetrating tells you how far it can get through things. The second type of radiation is more difficult to stop. So in other words, it's more penetrating. It is stopped by about half a centimetre of aluminium. And although it's affected by a magnetic field, so remember the alpha particles bending off to the right, then the beta particles would bend off to the left. This is beta radiation. It's much lighter than alpha radiation, and the particles have got a negative charge as opposed to a +2 charge on the alpha radiation. This is a symbol for beta radiation. The most penetrating of the types of radiation is gamma radiation. Gamma radiation goes furthest in air, it goes a long way in air, and also it goes through aluminium. But it will get stopped by lead. Gamma radiation is not a particle like the other 2. Gamma radiation is a wave. That means it's just pure energy, which goes up and down as it goes through the air. And because it's got no charge, and it's got no mass either, it just keeps going. And it's very, very difficult to stop. So gamma radiation is the most penetrating. It has no charge, and it has no mass. And it's not affected by a magnetic field.
Okay. So it's important that scientists understand the properties of these because we use radioactive materials in certain industries. We use radioactive materials to generate power, sometimes in nuclear power stations. And also, as we've said already, we use certain types of ionizing radiation for medical uses, such as gamma rays for cancer treatment, X-rays for medical imaging. And we'll be looking at some of these techniques in more detail over the next few lessons. Okay, so just take a moment to check what you've understood so far, please, by looking at these 3 questions, jotting down your thoughts. The video can be paused while you do that. So for question 1, the 3 types are alpha, beta and gamma. For question 2, to block a beta source, you would use aluminium. And for question 3, ionizing radiation can damage the DNA in the cells, which can lead to problems like cancer. scroll past that one. No, I'm not. Okay, so this is a really high level exam question, but we're going to have a look at it. So we've got OCRA Industries have an unlabeled radioactive source. One of their scientists needs to find out what radiation it is emitting. So she set up her equipment. So the radioactive source is set up on one side of the room. She will use some material as an absorber here, and then she's got a detector here. So a detector will pick up any alpha, beta, or gamma radiation that's getting through the material. So looking at her results, with no source in position, in other words, with no radioactive material here and no absorber, the detector is reading 38 counts per minute. Okay, so it's counting radiation in the air 38 times a minute. That's how often it's picking something up. So this is basically a measure of background radiation. We've got no special source, no absorber, just background radiation, providing a reading of 38 counts per minute. If she puts the source in position, but no absorber, then a reading of 2,500 counts per minute is picked up by the Geiger-Müller tube. If she puts paper in front of the source, then the count per minute is 2,498. If she puts aluminium in front of the source, then the Geiger-Müller counter makes a reading of 1,795. And if she puts lead in front, the count drops to 40. Use the information to identify the type or types of radiation emitted by the source. Give reasons for your answer and a clear explanation of why you eliminated the other type or types of radiation. The quality of written communication will be assessed in your answer to this question. So you need to use these readings and the information about the materials blocking the readings to work out what type or types of radioactive materials there are in this source. So is it alpha, beta, gamma, or a combination? So look at the notes that you've made and spend a couple of minutes trying to work out what source or sources, alpha, beta, or gamma, are here based on these readings. So pause the video while you do that, and then I'll go through the thinking behind the question, or the answers rather. Okay, so this is a sort of classic 6-mark question. So let's have a look at our information. So we know that there's 38 counts per minute of background radiation. If the source is present, we've got a much higher reading. If we put paper in front of the source, then the reading doesn't really change. That means that paper is not stopping the radiation. So we know that alpha radiation is stopped by paper. That tells me there is no alpha radiation present here, okay? Because these two readings are practically the same. 3 millimeters of aluminium in place does stop some of the radiation. So aluminium stops beta. So that tells me that some of this radiation source must be emitting beta radiation. When we put lead in front of our detector, the lead blocks all of the rest of the radiation. If you look at this reading here, it's pretty much the same as the background radiation. So I reckon much of this radioactive source was emitting gamma radiation with a little bit of beta. Okay, so just to show you that in the form of a mark scheme, these are the sorts of points you hopefully identified. I'll let you just read those through. So if you've come up with any of those points, that would be a mark each, so up to 4. And then with this question, the extra couple of marks would be for the quality of your written work. But even if you wrote that in bullet points, you get 4 points. Don't be put off by 6-mark questions. You don't have to write loads. They give you loads of paper, loads of lines, so you've got room to make mistakes. But actually, you can get well over half marks on these, even just by writing in bullet points. Okay, that is all we need to do on Alpha Beta Gamma for today. Thank you.